Changes of state. In this lesson, we'll talk about what happens to the particles of a solid as it melts. We'll talk about melting and freezing. What happens to the particles of a liquid as it vaporizes. So in that portion, we'll talk about evaporation and boiling along with condensation. And then finally, we'll talk about what happens to particles of the solid as they sublime. So we'll talk about sublimation in that section. To start out, let's look at this graph. The graph is of a temperature of a small pot of water on a stove. That pot of water is set at high heat. So question number one, how long does it take for the water to start boiling? And if we look at the x-axis, that measures time. So this question is asking for the length of time it takes for the water to start boiling. So looking across the x-axis, we go from 0 over to approximately 2. It's a little bit shy of 2, so it's approximately 1.8 minutes to reach the boiling point. Number 2, at what temperature does the water boil? So in this case, we're looking for temperature, which is measured in the y-axis. So if we look up to the point at which boiling starts, that is 100 degrees Celsius. So the answer to number 2 is 100 degrees. It's also important to note that the boiling temperature of water is 212 degrees Fahrenheit. So 100 degrees Celsius is equivalent to 212 degrees Fahrenheit. And finally, number 3, does it take more energy to heat the water to 100 degrees Celsius or to boil it? Well, if we're looking at this graph, and the graph shows that the pot of water is set on high heat for, it looks like a total of about 14 to 15 minutes, the vast majority of that time is spent in boiling. So the answer to number 3 is it takes more energy to boil the water because you have to heat it longer. So there's a lot longer period of time where the water is being heated during the boiling process. It only takes 1.8 minutes for that water to reach the boiling point. It then stays in the boiling, for about 12.2 minutes. What happens to the particles of a solid as it melts? Particles of a solid have more thermal energy than particles of the same substance in solid form. So as a gas, the particles have even more thermal energy. A change from a solid to a liquid involves an increase in thermal energy. So we have to add thermal energy. A change from a liquid to a solid is just the opposite. It involves a decrease in thermal energy. So we'd have to take thermal energy away. And for that to occur, usually the external environment takes some of that thermal energy away. Another example of this would be with our fish tank. The chiller on our fish tank, it takes thermal energy out of the water. So that device, the chiller, it is responsible for removing thermal energy from the liquid water that is found inside of the tank, and then it transfers that thermal energy into the air around the tank. So that's why whenever we walk into the back room near the salmon tank, we'll notice that the temperature is slightly warmer in air than in the other room. Simply because that chiller is continually releasing the heat energy, the thermal energy that is inside of the tank out into the atmosphere outside the tank. Melting. Melting is the change in state from a solid to a liquid. I'm sure many of us have seen this process occur during a nice hot summer day. You have ice cream. As the temperature increases or as you hold that ice cream cone out in the higher temperatures, you notice it starts to melt. So in pure crystalline solids, melting occurs at a specific temperature called the melting point. Because the melting point is a characteristic property of a substance, chemists often compare melting points when trying to identify an unknown substance. So we can actually take a substance that is not known, we can have it frozen or in solid form, and we can measure the temperature at which that substance melts. The specific temperature at which melting occurs will help to identify what that substance is. Water, for example, the melting point of pure water is 0 degrees Celsius. that equals 32 degrees Fahrenheit. What happens to the particles of a solid as it melts? So the energy needed to melt ice comes mostly from the air around it. So at first, the added thermal energy makes the water molecules vibrate faster, which raises their temperature. At a solid's melting point, its particles vibrate so fast that they break free from their fixed position. At 0 degrees Celsius, the temperature of ice stops increasing. So as melting occurs, once you reach 0 degrees Celsius, that substance will actually stay at 0 degrees Celsius for a long period of time until the process of melting completely stops. So any added energy continues to change the arrangements of the water molecules from ice crystals into liquid water. So the polar bear is kind of hanging out on top of this iceberg. He doesn't really want to get down into the water because melting is occurring. So all of the water that is directly around that iceberg is being maintained at 0 degrees Celsius. The water temperature cannot increase until all of that ice goes through the melting process. So as the temperature around that iceberg increases, as it absorbs thermal energy, the thermal energy will cause the ice to melt. And remember that the thermal energy is being absorbed from the surrounding environment. It could be from some of the water that is outside or around that ice, and some of the energy could be also absorbed from the atmosphere. So, looking at these two pictures, identify which circle represents the molecules of water and which one represents ice, and write it directly below each circle. So which one represents water, which one represents ice. Freezing. The change of state from a liquid to a solid is freezing. At liquid's freezing point, its particles are moving so slowly that they begin to take on fixed positions. When a liquid is put in the freezer, it loses energy to the cold air in the freezer. The water molecules move more and more slowly as they lose energy. And over time, the water becomes solid ice. As that water continues to lose more and more energy to the external environment, it takes on the crystalline form that we know as ice. When water begins to freeze, its temperature stays at 0 degrees Celsius until freezing is complete. So much the same as melting, it's maintained at 0 degrees Celsius until freezing is complete. The freezing point of water is 0 degrees Celsius. This is the same as the melting point. What happens to the particles of a liquid as it vaporizes? Puddles dry up from the process of evaporation. Many of us have seen this before. After a good rain, we'll have puddles on the ground as the external atmosphere gains heat energy or gains thermal energy from the sun. Those puddles will actually absorb that thermal energy. That thermal energy will promote evaporation, and those puddles will slowly dry up. So the water droplets that have been evaporated, they can then condense in the atmosphere to form clouds. Evaporation and boiling. The change in state from a liquid to a gas is called vaporization. Vaporization occurs when the particles in a liquid gain enough energy to move independently. There are two main types of vaporization. Those two types are evaporation and boiling. So we've seen boiling anytime we cook spaghetti or maybe macaroni and cheese. We boil a pot of water. You can see small bubbles that continue to come out of that liquid. That is boiling. Evaporation only happens at the surface of a liquid. So the fish tank, for example, has a large amount of evaporation that occurs at the surface. Many people actually put tanks inside of their bedrooms or inside of their homes to promote evaporation, so that then the atmosphere inside of the home has a large amount of water content to it, has a lot more water vapor floating around in it. This helps to keep people's skin from drying out and cracking. A lot of people that get bloody noses on a regular basis, that occurs during the winter times typically. It's kind of a seasonal thing, and it's due to the lack of moisture in the atmosphere during that time of the year. Vaporization that takes place only at the surface of liquid is called evaporation. A shrinking puddle is an example of evaporation. Water in the puddle gains energy from the ground, the air, or the sun. The added energy enables some of the water molecules on the surface of the puddle to escape into the air or evaporate. Vaporization that takes place both below and at the surface of a liquid is called boiling. When water boils, vaporized water molecules form bubbles below the surface. The bubbles rise and eventually break the surface of the liquid, and then that water vapor is released off into the atmosphere. The temperature at which a liquid boils is called the boiling point. And as with melting points, chemists use boiling points to help identify unknown substances. So we can take a liquid, we can boil it, and the temperature at which boiling starts would help to indicate what that specific type of liquid is. So inside of your notes, looking at these two pictures, please identify which one is evaporation and which one is boiling. Hint here, probably looking for bubbles throughout the column to help identify boiling. And remember, evaporation is only going to happen at the surface of a liquid. So the one on the left is evaporation, the one on the right is boiling. Also notice there's a large amount of heat energy being supplied to the boiling flask of water. Condensation. Condensation is the reverse of vaporization. The change in state from a gas to a liquid is called condensation. You can observe condensation by breathing onto a mirror. Many of you, I'm sure, have done this before. Or even breathing onto a bus window on a cold morning. And then you can kind of write your name in the condensation that's there. Sometimes if it's cold enough, the condensation will refreeze, leaving your name stuck there. So when warm water vapor on your breath reaches the cooler surface of the mirror, the water vapor condenses into liquid droplets. Condensation occurs when particles in a gas lose enough thermal energy to form a liquid. So contour trails with jets, this is a perfect example of condensation. What happens is the contour trails are created due to the jet's engines actually heating the air. As that warm air is heated, it comes in contact with the cold air outside of them. When warm air comes in contact with cold air, it promotes condensation. So those contour trails kind of are left in the sky due to the condensation of water molecules that are found there. Now this is another picture of a jet that is moving so quickly that it's coming in contact with the atmosphere around it, causing friction with that atmosphere. That increases the temperature right directly around the jet itself. Clouds typically form when water vapor in the atmosphere condenses into tiny liquid droplets. So a picture here of condensation occurring. So when the droplets get heavy enough, they fall to the ground as rain. Water vapor is a colorless gas that you cannot see. The steam that you see above a pot of boiling water is not water vapor, and neither are clouds or fog. What you see in those cases are tiny droplets of liquid water suspended in the air. Here's another example of condensation occurring on a spider web. You can see the small droplets of water sticking to the web itself. What happens to the particles of a solid as it sublimes? In places where it is cold, snow may disappear, even when the temperature stays well below freezing. Sublimation occurs when the surface particles of a solid gain enough energy that they form a gas. So a picture here shows a really cold location. You can see the snow all over everything. Sublimation is going to occur in this location. It's so cold that melting does not occur. So during sublimation, particles of a solid do not pass through the liquid state as they form a gas. One example is the sublimation that occurs with dry ice. Dry ice is a common name for the solid form of carbon dioxide. At ordinary atmospheric pressures, carbon dioxide cannot exist as a liquid, so instead of melting, solid carbon dioxide changes directly into a gas. You can see that occurring right here in this picture. As it sublimes, the carbon dioxide absorbs thermal energy. Usually that thermal energy is coming from the external environment. This property helps keep materials near dry ice cold and dry. For this reason, using dry ice is a way to keep the temperature low when a refrigerator is not available. Many people use dry ice during the camping season. They put it inside of coolers. It lasts a very long period of time inside of those coolers. And the really nice thing about dry ice is that because it doesn't turn to a liquid, it doesn't get all of the materials inside of your cooler wet, the way that ice can. Some fog machines use dry ice to create fog in movies and at concerts. And when dry ice becomes a gas, it cools water vapor, then condenses into a liquid, and this forms fog near the dry ice itself. Why do substances change state? So looking at this picture, this lake has frozen over due to the cold weather. As liquid water freezes, its molecules lose thermal energy. So how does the motion of water molecules change during freezing? The water molecules slow down and take on fixed positions. The air outside is so warm that a snowman is melting, much like the iceberg the polar bear was floating on. During melting, the water molecules gain thermal energy. How does the motion of the molecules change during melting? The water molecules speed up and they break free from their fixed positions. Wet footprints disappear due to evaporation. As water evaporates, its molecules gain thermal energy. How does the motion of the molecules change during evaporation? The water molecules speed up and they spread apart. This fills all the available space around those molecules. During the night, water vapor in the air condenses on a spider web. As water vapor condenses, its molecules lose thermal energy. How does the motion of the molecules change during condensation? The water molecules slow down, they come closer together. They are still free to move around one another in this case.